Okay, well, thank you everyone for your patience. It's a great pleasure to have Alan Hammond from Berkeley joining us and telling us about KPZ universality via Brownian Gibbs analysis.
Yeah, thanks, Evgeny. Thanks for everyone for joining. Yes, I was going to begin by just advertising a meeting that was going to occur at, I was going to show you live online, but my level of confidence in technology has now dropped. I'm just going to write down the stress of the technology means I've forgotten how to spell the word 8, but the 8 Pacific Rim
I think there is some resonance.
Oh, we need to kill the audio on.
I think it's fine now.
I think it was someone else.
Oh, someone else. Okay, so it might be, I do encourage people to jump in, but at the same time, maybe just a question of muting and then unmuting at the right moment. So the 8th Pacific Rim Conference in Mathematics, if you just Google that, then you'll see the website for a meeting that's occurring in early August. It was originally planned to occur in Berkeley. It's now moved online. It has 10 sessions in different areas of mathematics and a wonderful plenary speakers. It also has a very strong, very good probability session. So you might want to look at that. If you're interested, there's a very brief registration form on the site that you might consider completing so that we can get information to you about the probability session or whatever other sessions at the meeting interest you. So yeah, okay, so thanks again to Evgeny. Let me just give you a rough idea of structure. I'll be talking about the Brownian Gibbs technique, which is becoming, I think, a valuable technique in studying KPZ universal behavior. It fits within the framework of, it's obviously a field that relies profoundly on integral or algebraic technique and insight, and that remains true with this technique, but it comes with a flavor of probabilistic and geometric tools. I mean, one way of putting it is that the integral technique remains fundamental, but its role in another sense is somewhat limited to a certain number of inputs or black boxes. And this forms part of an endeavor that's somewhat broader than this technique to study KPZ universality via geometric and probabilistic means. So, for example, the solution of the slow-bond conjecture a few years ago by Redi Basu, Alan Sly, and Vadas Sidorovicius is another example of something in this broad framework. But a certain subset of this that has its own perspective and which is developing in interesting directions is the technique I'll be discussing. So the model I want to begin with is one that in some sense sits at almost the heart of the KPZ class in terms of LPP models, last passage percolation models, in the sense that if you think of universality in terms of the concept of a renormalization group operator, then you can think that sort of what happens is you take a given microscopic model with its niggly little details, and then the renormalization map takes you along a more or less smooth curve to a fixed point that has perhaps continuous symmetries and beautiful structures that emerge in the limit. Well, Brownian LPP is a model that in a certain sense, and this is related to the validity of this Brownian Gibbs property that I'll be describing, in a certain sense that trajectory to the limit is a perfect straight line, because the particular nice symmetry and property that I'm interested in is perfectly respected in the prelimit. So that makes it a very auspicious, is that the right word, choice for a study via this technique. So yeah, let me just, oh, by the way, the structure of my talk, I'll be giving in the first part of the talk definitions leading to this technique, and then I'll try to give some simple applications of it. And then I think we'll have a nice 10-minute pause. And this talk will go on somewhat, I'm afraid, beyond an hour. So, you know, if you want to drop out at that point, I certainly understand. I'll then go into a certain runoff second period in which I talk about slightly more recent and in some sense slightly more advanced aspects. So let me begin with Brownian large passage percolation. So I have these horizontal intervals that, let's say, begin at the origin and end at a given location x positive. And let me label the vertical levels 0, 1, 2 up to level n. Okay, so what I do is I attach to each level a nice independent standard Brownian motion. So we can have a bit of notation. This is B0, that's the indexing vertical level, and then that's the process. So this happens independently at every level. These things, as they're drawn here, I'm just kicking them off at the, just for reasons of hopefully clarity of presentation, I'm kicking them all off at their respective levels. Okay, so then what I have is another part of the structure of the problem is to have a so-called upright path that begins at 0, 0 and then moves through this system. So it's in the obvious sense, a non-decreasing path that moves up towards the end point at x comma n. So phi there, that's an upright path, and it's from 0, 0 to x n. Okay, so then that path receives an energy E via this random environment. So if I go to do something in red here, we can see the response somehow of the given phi to the environment. It sort of enjoys in some sense a ride along the environment, jumping from one level to the next in the highlighted black region, and then in a sense following the path. Just draw these sections that you have at the end. I didn't draw the Brownian motions there in the first place, but yeah, so you see what you're doing really is having that journey, and then the definition of the energy E attached to the path phi is the sum of the Brownian increments encountered along phi. Yeah, okay, so that's the underlying definition for a given path. And then we move to already a central definition for last passage percolation, which is to define M for maximum, MNX. That is going to be the supremum of the available energies for such paths. So the supremum of the energy of phi on these routes, phi an upright path, I won't write that, but from 0, 0 to xn. Yeah, okay, so that then is the path that maximizes that. It's not very difficult to see, is almost surely unique, and we call that the geodesic. And the question of its geometry and the energy that it actually has are central questions for studying last passage percolation. Okay, so I can generalize that in a way that's natural. Many of the things I say, I'm sure, are familiar to many in the audience. Forgive me for that. I think it is best to set the framework clearly to include everyone, and because it sort of gives a coherence, I hope, to the ideas of this talk, leading to the presentation of the Brownian Gibbs property. What I want to do is to generalize this, and this was related to the so-called RSK correspondence. Okay, well, I'll be defining that in a minute, but maybe first of all, let me do a sketch. Maybe I'll take k equals 3 here. So in the previous case, I somehow took k equals 1. What I'm now doing is considering an analog for the concept of the upright path, where I use 3 in an appropriate sense disjoint paths. So disjoint will mean that the paths have, they have these horizontal sections. If I draw a given path here, just focus on this one. It's quite fun in a way to depict it as a kind of staircase. The vertical sections here are not tremendously important, but okay, it's quite fun to draw it like that. That's an upright path. And then I can refer to the disjointness of two upright paths, two staircases, as meaning their horizontal sections are disjoint. That permits the paths to begin and end at the same points in some sense. So this is going to be a triple staircase that is a k=3 instance of this more general definition. So you see that will receive in the natural way a definition of energy. I will sum the increments of all of these. I won't draw all of them, but of all of these little sections of Brownian paths, sum the increments of those. That will be the energy you have for that triple staircase. And so with k being a general parameter, and I suppose it's capable of taking any value between 0 and n+1, n+1 being the number of vertical levels in this picture. So if I take the supremum of the energies as just verbally defined of k tuples of disjoint paths, upright paths, on the same route. So then that's a notion that specializes when k=1 to the geodesic energy, and otherwise it's a notion of maximum energy available in these systems. So yeah, okay, so what I want to do is now explain an important result of Neil O'Connell and Mark Yore that will already begin to make the kinds of connections I'm interested in illustrating. So let me define what will be a line ensemble. I'll be drawing plenty of pictures of those. It's a random system of curves that are non-intersecting, rarely building straight from the structure. So xn will be a whole system of random curves, and it will have an uppermost curve, in fact, with index 1, and it will be a processing positive x, and it will simply report geodesic energy. So you see I'm varying this endpoint x here and running up to it with the best path I can from this fixed origin. That point is moving, and then I'm reporting that value where this vertical extension is n or n+1. So, okay, what I then do, there's two ways I suppose I can record the formula in the general case. The kth curve in my developing system will be the difference between the maximum energy I can collect with k disjoint paths with these shared endpoints and what I can collect with merely k-1. Yeah, and then I suppose k can run up to n+1, and it starts in that particular definition at 2. And then, of course, that's equivalent to saying that inductively the objects are being defined in this rising k in such a way that the right-hand side terms are being defined inductively in such a way that it's true that the sum of the x's is equal to the m energy. So we can think of x n k x as being the it's an excess energy. When I add in that extra curve. So what's the best energy I can get from the k system, and what is its excess over the best energy I can get with k-1 curves? That's what this quantity is. So let me put that on hold for a moment and recall an important probabilistic object, Dyson's Brownian motion, which Dyson introduced in a fundamental paper at the beginning of the 60s, which made an important connection between random matrix theory and mutually avoiding systems of Brownian motion. So just m here is just a general parameter, positive integer, let me draw an example with 4 curves, perhaps. They all begin at the origin. They are Brownian curves, and they are being conditioned to avoid one another. That's what's going on here. So this is with m equals 4 the uppermost curve, and then the second curve, and so on. Yeah, so that then is, the notation would be that dm is defined over this domain and range, and it is an ordered system of m standard Brownian motions. They each begin at 0, and they are conditioned on a complete avoidance of one another at all positive times. So conditioned on mutual pairwise non-intersection. At all positive times. So it's a singular conditioning in 2 senses. The motions all begin at the same point, so the unconditioned motions will naturally hit one another immediately. And because the window in which we insist on non-intersection is infinite, even if they were to begin apart, they would inevitably meet. So you need to cope with those things by doing things like taking weak limits of neighboring less singular conditionings, and then the theory of the Dubage transform is a technique that permits you to make sense of this object. This is anyway an unambiguously defined, uniquely defined, interesting probabilistic object. So I've given you 2 objects, the xn curve process of excess energies from Brownian last passage percolation and Dyson's Brownian motion. So O'Connell-York says that those processes in a suitable sense are equal. Yeah, so the process, the excess energy process, xn, which is k in that definition, remember, can run up to n plus 1. When it reaches n plus 1, there's no choice of where to put the staircases in there, or just flat. That's the end of the system in that sense. So this is the domain of definition, curves real value. So that has the law of n plus 1 curve Dyson. Yeah, so you see, if I redraw a little bit of a Dyson system, and then treat this as the variable, you see this location x here. This point is the best I can do with a 1 curve in this system running from 0 to n times x here. That's the best energy I can get, that's that value. And then the sum of these 2 is the best I can do with, you know, I'll try and draw it on the same little image, not perfectly drawn obviously, but you know, the best I can do with a pair. So, and so this the second point is the axis. So it's not unnatural in a way that it's a decreasing process, and, you know, in terms of the economist notion of what is it, decreasing marginal returns. It's intuitive that as I add in an extra curve and ask what's the excess energy I can now achieve, that the pickings are becoming more sparse, more spare as the process goes on, as k rises. So it's perhaps intuitive that this is a decreasing process. So that's, okay, one element that will permit me, I could now tell you directly, I suppose, what the Brownian Gibbs property is, but in terms of the analysis that's been performed with it, there is another key ingredient beyond its mere definition that is somehow very relevant. That's the fact that it's somehow well adapted to problems involving universality and high-end limits of last passage percolation. So in order to have the framework set up in the right way, I want to define or perhaps recall scale coordinates for last passage percolation. So that involves recalling the you know, the 1/3 and 2/3 that we always see in KPZ, let's see how they come up. So in this model, so MNN, so we're now going on a diagonal route here of length n. So yeah, the best energy you can get on that route, it grows linearly in n. In this model, the growth rate is in fact 2 times n, I believe. And then if we ask though what the standard deviation of the geodesic energy is, it has order, that's essentially the same. It's not literally the same, but it's essentially the same as subtracting off the linear term 2n and asking what the order of the remaining quantity is. That is theta, that's a unit order random quantity, times n to the 1/3. Okay, so that's the 1/3 exponent of KPZ right there. And then I can ask a spatial question to get the 2/3 exponent. If I end always at height n here, but at horizontal location n, and I make a comparison with ending at n plus x, while I begin always at 0, so the geodesics come backwards. And by the way, they have a nice coalescent structure. Coalescence of polymers is in a way another nice geometric technique that has a certain value, but it's an aside here. What I want to do is to answer the question in terms of the energy. Let's ask the question, the geodesic energies on the 2 routes, which are denoted here. Let's say, with a fairly literal number here, let's say they have exact 50% correlation. Okay, this is supposed to be a question. When x is what? What value of x do I have to choose in order to achieve this unit order correlation bounded away from 0 and 1? Well, it's again a random, well, okay. It's anyway, it's on the scale of n to the 2/3. So here we see the 2/3 exponent of KPZ. And this, by the way, corresponds to the same scale at which this height, this coalescence height that we have here, is of order n. So it's sort of bound, well, it's of order n, and so is its complement, if you see what I mean. So you know, halfway along, as it were, you have the coalescence moment in a vertical sense. So you've got the 1/3 and 2/3 exponents of KPZ sitting right there. And then that provides a good background, I hope, backdrop for the a natural scaling I can perform on Dyson Brownian motion to express it in a scale coordinate system that will be valuable for studying universal high-end questions. So if I draw Dyson Brownian motion with a fair old number of curves here, it's kind of the watermelon picture. All right, so I'm supposed to have drawn that with, well, okay. I'll write n plus 1 because that's kind of the context, but essentially an n curve system, and that's the top curve. And then I'm focused on what happens at location n here. So there's a natural window I can draw here. It has sloping sides. That's in some sense a detail. The thing I want to focus on here is I want to draw a window here that grabs hold of the action. It's probably going to see the top curve of my window, and it's going to be kind of on the right scale to judge the fluctuations that go on. So you see, for that reason, I choose the window to have a height n to the 1/3 to reflect the typical behavior of the top curve. And then I want the window to also be informative and interesting in the other coordinates. So it's going to be, you know, what's going on at the left of the window is beginning to be meaningfully different from what goes on the right. So that's related to the scale I mentioned. This distance should be n to the 2/3. So a simple affine change of coordinates brings me to a situation that has a sense of independence on n and a degree of consistency and statistical settling down as n rises. If I draw a nice unit box here on the right hand side, this would be the scale picture. and I simply am going to choose the affine change of coordinates. We can make the, I won't draw it, I can make the center of that box the origin of the new coordinate system. So there's just going to be an affine change of coordinates that is going to translate that parallelogram into that square. And so what happens when you do that is your curves get carried along in this ride, and that's the top curve. The order of the curves is certainly preserved by doing this. This is going to be the scaled, the counterpart of the process on the left. And then naturally the other curves come along as well. Now they end up being at unit distance from one another and having a unit standard deviation for their height at a given point. They are locally, okay, what's going on at the level of Brownianity? So this is important. So on the left, the underlying constituent processes were standard Brownian motion, diffusion rate 1. And then we've actually undertaken a change of coordinates with 2/3, 1/3 in the exponents that respects the fundamental symmetry, the x squared equals t symmetry of Brownian motion. So the view is that we shouldn't have changed the local diffusivity of the Brownian motions by doing this. They will remain in their local structure, standard Brownian motions. They will now follow, in fact, a parabola. Now, I might be, I'm going to write this parabola. I should mention that there's a convention that the process we're talking about here after parabolic adjustment, that's the Airy 2 process, has a diffusion rate 2. So yes, all right. Anyway, this isn't very important that perhaps at this level of detail, the precise parabola may have a slightly different coefficient. Yeah, okay, so globally parabolic, that's what I want to say, and locally Brownian. This is the object we're talking about. So, and what is its interpretation for LPP, for scaled analysis, high-end analysis of last passage population? So for that, let's go back to the original picture of beginning at, or ending at n in one case. I won't draw it very carefully now. Coming back to 0. And then you see, we identified it's rather natural to consider a companion route with n to the 2/3 displacement. So that goes on its own journey and coalesces, 50% of the way along in a vertical sense. That's the basic picture. So I can map that. I can map that picture in a way that's conceptually really exactly the same as for the other picture. I will keep the origin where it is. The starting point will come here, and I will move n comma n so that it is exactly 1 unit above the origin. So now this, there's a sense of, in a certain sense, I want to say time going in this direction and following the path upwards. And then I want to move this point to be 1 unit to the right of here. So that involves doing a shear map and then squeezing space by n to the 2/3. So then what I will get in, if n is very large, I'll get these rather continuous curves, and they kind of look like this. They'll actually, if I draw more of them, have a nice tree structure related to the coalescence. That's fine. So then if I take a generic location x here, just as, okay, so there I did a transform that starts talking about scale descriptions of these geodesics. Scale geodesics are sometimes called those polymers, although that term does have other uses. But naturally enough, that's to do with the 2/3 side of the situation. KPZ has its 1/3 exponent. And then that shows up if we talk about scaled geodesics and their energy. So scaled geodesics have scaled energy. Yeah, so, and then quite simply, the top curve in the scaled Dyson, this curve right here, up at the top here, is reporting the, its value here at x is reporting inappropriately judged affine change units, the energy on the route that in the scaled sense goes from 0, 0 at the bottom of that tree up to x comma 1. And then you can also have an interpretation for the some of the top 2 curves, which is that you're drawing a structure like this, then the best you can do with this kind of disjoint, except at the endpoint structure, that's the sum of these 2 points. So you have an object that is, in a way, quite a vivid probabilistic object, and it has this rather direct and geometric interpretation for scaled coordinate last passage calculation. So I now want to, okay, let me move towards the Brownian Gibbs property. Let's look at the Dyson system again with just maybe 2 or 3 curves. It makes no difference how many. Suppose I had sampled the whole thing, but I had left out one section here, just the deterministic endpoints and for definiteness, the top curve. So if I show you that picture and say, hey, look, this was sampled from a Dyson Brownian motion, you can see how many curves it has in total. And then we actually wiped away the information in this section. What would be the conditional distribution from your perspective of what is missing? So it's very intuitive what the answer to that question is. And it's related, for example, to the Levy construction of Brownian motion to see why it's true. I'll just be explaining it and relying on intuition. A careful proof of this statement that's been used for a number of years was recently provided in a paper of Yevgeny and Konstantin that I may briefly discuss later in the talk. So you could certainly look there for details. Anyway, the view is that the correct conditional distribution, if I go for a rejection sampling approach, I draw in a Brownian bridge with these endpoints going where they need to, and then I check if I meet the curve below. And then if I do that, I reject the sample and I redraw until I get one that works. But all I'm saying is, okay, it's Brownian, the correct conditional distribution is Brownian bridge with the right endpoints conditioned to remain above the curve below. Now, how does that interact with, if that picture is somehow sitting, it's somehow natural to think of it sitting around here, resamplings occurring inside this somehow key box for scaling problems. How does that relate to, how does it transform under the affine scaling map that brings us into scaled coordinates? Well, the answer is straightforward. It survives the transition. If I do the same type of experiment with these locally Brownian but globally parabolic curves that we see in the scale description on the right-hand side of this, where's it gone, of this picture, I respected the parabolic invariance of Brownian motion in doing my affine change of coordinates. So Brownian maps to Brownian under that. Avoidance conditions are respected. So this same rule of resampling, conditioning to remain above the curve below, and then getting the correct conditional distribution for the missing material is respected in the scale picture. Okay, so this is something that think of n as being rather high in this picture, but given. But let me take n to infinity in a statistical sense to obtain a true limiting picture. That is the parabolic airy line ensemble. It's the airy line ensemble in its curved form. And now all finite size effects and considerations of where the origin originally were have drifted off to negative infinity, and we have a perfectly an object with symmetry. It's defined on the whole of the real line now, and when you add the parabola in and get the airy line ensemble, you have an object that's stationary. So the overall view then is that the Brownian Gibbs property should also survive the passage to the distributional limit here, because you should think that the convergence that one would expect from the finite n to the limiting n here should be in the sense of what's called weak convergence in a locally uniform topology. So that means, if I take a compact region of space here, I'll be able to do a coupling so that the pre-limit and the limit have with very high probability less than epsilon disagreement in the suprema norm anywhere within the window, this kind of stuff. So that should mean that the view is that this is just a view of the overall technique at some level. So the BG property, Brownian Gibbs property, should survive the passage to the high-end limit. So then the parabolic Airy ensemble comes equipped with this nice resampling. So when it sits there in that role, it becomes a valuable technique for studying, well, the Airy LE itself. The Airy LE, the theory that I'm talking about here was, I suppose, developed in the paper with Ivan Corwin that, well, it introduced the Brownian Gibbs technique in print, although the idea had been proposed at some level in discussions between Andrea Kunkov and Scott Sheffield before that. But in print, this is where it made its appearance. And we used it to, in fact, give a construction of the Airy line ensemble as a space of continuous random ordered curves, whereas before it had been understood in its finite distributional characteristics, very nice determinantal formulae for that by Prahofer and Spahn's work around 2001. Anyway, so that's all in the middle of my sentence. So what I'm saying here, even at that point, that was an aside, even at that point, it was clear that the Airy LE was an important building block and part of the structure of KPZ universality. And since that time, it's become, in a new vivid sense, even more central in a way, because Dalvern, Ortman, and Virac have demonstrated that one can actually read off richer KPZ structure. You see, at the moment, everything I'm saying in scale coordinates is to do with starting at the origin and running up to this line. And then the Airy LE top curve in its parabolic form is telling you what this scaled energy is. But there's a nice transform that's been identified by DOV that allows you to, in fact, read off more general information where both endpoints are variable. So anyway, understanding the Airy LE via its Brownian Gibbs property is something that very much speaks to important and pretty general problems about scale descriptions of LPP, and with that, the KPZ universality class at large. I might be able to say a bit more about DOV later in the talk. That would be after the break. It is something that, in terms of the ideas of this talk, I suppose I just want to say that it's technically undergirded by a work of Dalvern and Virac, in which the Brownian Gibbs property is used to give a degree of control deep down in the Airy line ensemble that's needed to set up their description. Okay, so in some ways it's, I hope I've succeeded in communicating the sense that the basic property that the BG resample property is rather straightforward. The reasons, I hope, why it moves into the scale description and then passage to the higher limit to the Airy line ensemble are intuitive and I hope appealing. The actual analysis that's been undertaken with it at times has become a little complex. And so what I want to do, I suppose, leading up to this break we're going to have, is tell you actually about two or three, let's see how time goes, pretty simple applications that give nice conclusions. So level of detail here won't be 100%, but I will, the techniques are simple, and I will, I think, be indicating, I hope, the fundamentals here. So let me begin with that. Are there any questions before I move on to this slightly different phase of the talk? Please do jump in now.
I had a question real quick, if that's okay.
Yeah, sure.
So I know there's certain exceptional points where you don't have unique geodesics between the 2 points, and does that cause a problem when you're looking at these tree structures? Is it easy to get around those exceptional points, or is that a major issue?
Yeah, that's a good question. It's in a way related to the first of the applications. Yeah, so you're right that there's a certain imprecision. In fact, when I talked about a tree structure, the origin here is fixed, and then if I take a generic location upstairs, it is not difficult to see that for a generic given location, it's not difficult to see, as you say, that we have an almost surely unique path. But equally, it's not hard to convince yourself there will be exceptional locations where we don't have uniqueness. You can basically see that by scanning along this path, and then it will in some sense jump from one little canopy to the next at certain moments. You'll have a theory like this. It's related to things that, for example, Chuck Newman's worked on around the Brownian web, which is, if you do this sort of system, if I just run from every point in the plane a nice Brownian motion, and then I run from another one, and then when they meet, I have them hook up. So you see each one is following a Brownian motion. Then I can sort of build an object. I want to say build an object by taking a countable dense set and using some completion tricks to build a nice object like this. And then actually after you've done that, you have a kind of a dual picture in which you can have other dual curves running backwards. And now form a Brownian web coalescing Brownian system running the other way. But there are some topological challenges to making sense of this picture and converging to it. There are of necessity points in this picture where you don't immediately join up. You cannot say those things in the, by the way, in the Brownian web, you have a nice piano curve that runs between the forward and backward things, and it's one of the values of the Brownian web is that you have, that's a very nice object, because that, by the way, has a 2/3, 1/3 exponent rule to it that has an interesting connection to KPZ. It's the scaling limit of the true self-repelling motion, which is to do with weakly self-avoiding walks on the integers. And you can do that stuff here with, there is a dual tree that in some sense has the same law. And it's fun to study these aspects and the piano curve between them and the non-uniqueness points and how you set up the topology. All of these things are interesting questions that a little bit has been done in a way, but they've never really become the focus of attention. It could be a good area to somewhat expand. That was a somewhat broad and unfocused answer to your question, but does that sort of respond to some aspects of it?
Oh, that's great. Thank you.
Sure. There are Hausdorff dimension questions about non-uniqueness. Maybe I could comment on that. It's actually related. Well, a different aspect of non-uniqueness is related to just three simple BG applications, I suppose, is the quick way of writing the title for this section of the talk, but we'll run up to the break. So, okay, the first application has a certain connection to the question. It's a slightly different aspect of uniqueness and non-uniqueness questions. So maximizer, or sometimes people use the word argmax, Johansson's maximizer uniqueness conjecture. So rather than just directly state the conjecture, let me provide the context. And that is, again, a scaled description of the model. So here is my scaled path. It has its scaled energy, like I've been saying. We have this effectively tree structure. So below this level X, as I've been saying, I can plot the scaled energy, and I do that for each point. They form a process that is the parabolic manifestation of, with parabolic curvature, that is the Airy-2 process introduced by Prohofer and Spohn at the beginning of this century. Okay, so that is offering the scaled energy profile for the route from 0, 0 to x1, which is depicted right here. Yeah. So in those terms, yeah, Johansson's conjecture is a very specific conjecture about this process. It says its maximum is only attained once. This point is unique, almost surely. That is Johansson's conjecture. And that, of course, is intended to indicate the maximum level. So why is that a conjecture that he was led to make? It's because it has a natural interpretation for LPP. If I go point to line, as the expression goes, I start at the origin and go up to level 1. Now, I've been talking about, hey, let's go to a given point and see what's the best energy we can get. That's been the geodesic energy in its scaled or unscaled form. But let's say now, hey, let's go up to that line. Just get me the best energy you can. Don't care where you finish. What's the geometry of that outcome? Is the geometry of that outcome, you're definitely going to one point. There's only one point that you're attracted to. Or is it possible that there's 2 or even more points that give you exactly the same outcome, which is the best? So Johansson's conjecture is saying almost surely it's the former scenario and not this one. It's the point to line maxima will go to a well-defined unique point. So it's a natural enough geometric question about LPP. So this object has been anticipated to be, you know, a Brownian object locally or indeed in unit order windows. So it's completely natural to believe that it will have its maximum at one place. It would be a pathology to hit a given level and then come back to it, given obviously the very disordered local movement in Brownian motion. This would be a pathology. But the kinds of formulas that were classically, maybe I shouldn't, I don't know, what had been harnessed before. I mean, beautiful formulas with detailed information, but they were somewhat rigid. And certain questions, the kinds of counterexamples you might talk about in a grad class in analysis or whatever, to do with the difference between finite dimensional convergence and stronger forms of convergence, weak convergence and local uniform sense. The kinds of counterexamples are that you have maybe a very, very thin peak that manages to pathologically rise to precisely the level that you had before. And then somehow, while I'm suppressing some parameters here, there's a parameter like n in this going on that's rising. The view is that maybe this is getting very narrow in n. So if I understand the probabilities of going through these intervals and maybe I have a nice determinantal formula for it, they could fail to notice the pathology of a very narrow thing that isn't likely to see any of these horizontal coordinates. Yeah, so this is the kind of you know, the beginnings of the sort of probabilistic geometric analysis. How can we rule out this pathological behavior that no one would have believed could occur? So yeah, so I mean, in a way, another way of advocating the technique is to say that sometimes you're studying an object of interest, here the parabolic area 2, and it's a good technique to find a richer structure, perhaps a higher dimensional structure in which you can embed your object, and then the overall structure of which what you're interested in is merely a projection. Is, you know, the richer structure has some nice symmetry or property, in this case a resampling property, that the individual component of it, the top curve in this case, lacks. So that's exactly what we're doing. I'm taking, let me call it L. Okay, that's the curved unit, I'll call it L. That's anyway the top curve, that's the parabolic area 2. I embed it in the proof of the conjecture in outline, and this goes back to the work with there are, by the way, a couple of other nice proofs out there of the conjecture. I'll focus on this. Yeah, so I'm embedding in the ensemble and using that as a technique of proof. So it's going to be a BG resampling approach, of course. So as any analyst will say, you know, if you want to show something that's known to be non-negative is 0, you want to show the probability of at least 2 maximizers I want to be showing is less than epsilon for any positive epsilon. That's the task. So an epsilon of room, as Tao calls it. Yeah, all right. So that allows me, that little epsilon of room allows me to compactify things a bit. So I can choose, or anyway, this is actually an intuition that, to make precise, you actually somewhat tied up with the ideas in the proof. So yes, this isn't going to be a proof in all its details, in fact, but it is going to communicate, I think, the main idea. So I'm going to choose K to be, this is going to be, in effect, a long compact interval. It's going to be chosen large enough. The view is that we will undertake a BG resampling in its basic guise, omitting the top curve between minus K and plus K and keeping everything else. So you're the observer, you get to see that. And if K is large, there'd actually be a fairly pronounced hill to jump over coming from curvature. Anyway, I choose K so large that the probability that I've missed the maximizer because it lies outside this region is less than epsilon, or if we're careful, less than epsilon over 2. Now, it's quite intuitive that that would be the case given the nature of the curvature, although it does involve a certain compact uniform control that one can gain, for example, via BG, another instance of BG resampling. I just want to take it as given, or I hope I may, that the probability of having a maximizer outside a large compact interval is small. So yeah, well then it's at this stage, I am drawing in my Brownian bridge with the given endpoints. I'm conditioning it to remain above the curve below. But that is a positive probability conditioning because this structure, which we've already set up, that's the view, is supported on continuous, non-intersecting curves. So you see, if I have something that's almost surely happening for the candidate Brownian motion, which is tested on the non-intersection requirement, that property will automatically transmit to be almost surely true for the outcome, the real deal conditional distribution. And that's true for Brownian bridge. If I take Brownian bridge and just to simplify, I'll work with standard Brownian bridge. It has its maximizer almost surely in one place. You can actually prove that, by the way, in a way, if you ask me right now to prove that, the notion of how I would do it would be to use a BG resample. I would say, well, okay, I have to rule out 2 or more maximizers. The countability argument means that I can choose 2 given intervals with rational endpoints. Or maybe I only need 1, actually. I'll freeze frame the entire picture outside this interval and resample here. And then, yeah, well, the view is that do I hit the maximum outside? That's a given level, but it's easy to see that the maximum level of the bridge has a continuous distribution and doesn't hit points. So you see that way you can use, in the same ideology, you can see why it's true that the simple statement that Brownian bridge doesn't have 2 or more maximizers. So yeah, well, that was maybe a little fragmented in the way I presented it, but you see that's small, compactify, focus on a compact interval, and then transmit almost sure property from free Brownian bridge with given endpoints to real deal conditioned process because positive probability of success. So so Johansson's conjecture is in a way a fairly simple outcome given the technique. The technique does require some setup to actually argue that the original paper with Ivan worked quite hard in a way to prove that you could pass to the limit. That proof has now been simplified, both in my work and by arguments of Darverne, Ortman, and Vierak. There are simpler constructions now of the area line ensemble. So that was anyway the first application. Any questions about that before I move on to another one?
Is the second one short?
Is the second one short? Oh, how are we doing for time? Are we?
We're about 1 hour in.
About an hour in. Maybe I'll just. You know what? I think I don't want to overuse people's time. I think in a way, from a practice talk, the third one is fairly similar. Let me just give you the second one, and then we'll have a break. Yeah. So no Big Macs. Okay. So this is related to integrable input. So you see, if I take this is an object whose this top curve and it's parabolically adjusted. It's an object whose statistics are in fact independent of x, and it's very classical Tracy Whittam GUE information that there are two problems I can ask. What's the upper tail? The upper tail is behaving like this, independently of x, with a 3/2 power in the exponent. And then the lower tail is with a power of 3, in fact. This is what I mean, in a way, by limited but essential use of integrable input. This is an example of arguments that begin being fed this information. Where can we go with it? I just want to give a rather simple example of where we can go with it, and it's not particularly shocking and can be obtained by integral technique anyway, although the underlying technique can give somewhat more general conclusions. I just want to indicate how we can move from one-point information to something that involves processes more. If I take the very highest level you can reach, that we've already been addressing the x coordinate in the previous part, I just want to argue a claim that the same type of, with adjustment of constants, the same type of conclusion is valid. No Big Macs, an absence of exceptional behavior. You cannot have the kind of picture of a brief jump like that. I mean, yeah, okay, so I'll be fairly brief here. I think it's enough basically to argue, it's intuitive, it's enough to argue that the biggest you can do in a given compact interval is controlled, because there's only finitely many compact intervals near the origin, and then apart from that you have parabolic curvature. So if you had a tremendously high point here, imagine h is rather a high level, how can we use BG sampling to say something weird is happening here? Well, the kind of argument I want to give is, I'll take a point out here, which is 1, yeah, and then I'll control here. I know lower tail, so I know it's typical. My value for this process here is above minus h/2. So, all right, if I had that tremendously high maximum over on the left, what I could do is search for it in the sense of a stopping time argument from the left, and then, if it occurred, I would reach it. So what I want to do is kind of a strong Brownian Gibbs resampling, where I randomly wait to see if I hit that level h and stop right there in my search from the left to the top curve. If I do so, then I'll sample the right curve to the right of the deterministic location 1, and then I'll draw in the rest of the process. Okay, and then what I want to do is do a bit of a BG resample on the remaining interval. Now the view is that although randomly selected, I didn't have to peek inside and cheat the unknown region. I didn't have to look at that in order to see what the outcome was. So that means essentially that the BG resample remains valid in this special random region. So what I have then, if I just draw ordinary Brownian bridge between these two levels without any conditioning, it didn't in this case, but it might have hit the curve below. Then I can do a coupling. I mean, this is a monotonicity lemma that has to be proved, but it's intuitive that the real deal conditional distribution can be coupled to sit above that, because it gets a push from below in a way that the free Brownian bridge does not. So you see, then you've got a situation where that Brownian bridge, you see, it's at level h here, and it's above level minus h/2 here. So if I take the point 0, 0 is somewhat closer to this point than it is to this point. So the value of the pure Brownian bridge process at this level has a 50% probability to be above a level which is the average of h and minus h/2, and that average is in fact h/4. And then the real deal resample is, if anything, slightly above that. It's coupled to be above that. So what that means is that basically, if you get this event that you're very high on the interval from -1 to 0, alongside a completely typical event relating to your position on the right, then you have a 50% chance of, at a given deterministic location 0, the top curve is bigger than something that's still really high, h over 4. So you've turned, by that argument, I won't write down further details of it, the ideology of the argument is by the BG property, the potentially exceptional, having a peak that could maybe just occur in a tiny instant at an exceptional moment of time, it becomes the typical. I.e., you can't really have those peaks. Whenever you have a peak, it is typically associated to an extended period of being high. And then, you can't hide from that. You can't hide from that with 1 point information. This is some boring deterministic time that just sits there in that fairly average interval. And it says, hey, I've noticed you've gone really high. You can't hide from us. That's the style of the argument. Yeah, so I don't want to overuse time. I completely understand if people have other things to do. Let's have a bit of a break anyway. And then after that, I'll talk for, I don't know, 20 more minutes or something about more recent and in some sense slightly more advanced things that the BG technique has done. Thanks a lot for your attention.
Okay, so let's come back at 2:15. Resume then.
If anyone has any questions, of course, just feel free to shout out. By the way, I hope we haven't got this. My screen has now gone back to, what are you now seeing?
We are not seeing your iPad.
Oh, you are seeing my iPad?
I am not.
Oh, you're not? I think I will call in the troops again on that. Hey. So we've got still got a couple of minutes. Well, there's a couple of minutes before we come back. Is it that inactivity on the iPad leads it to?
I don't think so. I mean, I don't know.
What was it you did?
Well, before I messed it up because
Okay.
I closed accidentally your Zoom. Just say start broadcast.
Oh, okay.
And then you can go back. What is this?
Oh, great. Okay,
You
thanks.
just have to do it again.
Yeah. Hi, everyone.
I'm going to
So I think we can get started if you're ready.
Yeah, thanks everyone for getting back and for the second session that will be treating a little bit more advanced things. I haven't planned very carefully how long to speak for. I could speak for just another 20 minutes, or it could be a bit longer. If you have to leave at any given moment, please do. Yeah, so well, we'll see. So let's read a little text first, give a little context. The sun had not yet risen. The sea was indistinguishable from the sky, except that the sea was slightly creased as if a cloth had wrinkles in it. Gradually, as the sky widened, the dark line lay on the horizon, dividing the sea from the sky, and the grey cloth became barred with thick strokes moving, one after another beneath the surface, following each other, pursuing each other perpetually. That's the first paragraph of Virginia Woolf's The Waves. I want to, if we look at the airy line ensemble, we can think of the top curve as being relatively flat and forming a kind of crease on the horizon, with it being supported by, undergirded by a bed of further curves, with similar characteristics being attenuated as one approaches the bulk, and the kinds of incipient forces and tensions in perhaps Woolf's pictures of the waves reflects an idea that I suppose one can consider here, which is that can one do a dynamical update on the airy line ensemble that leaves the motion at equilibrium. This is related in a way to the Brownian Gibbs property. If I take a given section here and resample it, well, my picture is going to become a mess, but you know, I can resample and then I can have something at equilibrium. What I could also do is, if I wanted a more continuous update, I could start sampling different parts of it on perhaps rather short sections and doing a lot of updates so that the whole thing, the different curves chosen in propitious ways, so that the whole thing starts shimmering on me and then but staying at equilibrium. That idea is something that I haven't actually very thoroughly explored, but a cousin of that, and the connections in fact are of interest, we have been exploring with Shishendu Ganguly. In forthcoming work, we'll be treating a dynamical version of Brownian LPP, and that will be one of the themes. I won't have very much time to say about it, in fact, but it will be one of the themes for the second part of this talk. Okay, so before I get there, I want to, I suppose, review, in a way, where did the original paper with Ivan, I think it was 2014 it came out. It can be called at this stage, in a certain sense, basic BG analysis. I just want to kind of give you a rough characterization of the kind of outcome it achieved and locate that relative to more recent developments. So when I look at the picture I'm always drawing, the parabolic airy line ensemble, and I'm looking at a given interval here, perhaps it's -1 to +1. So I have this fragment of curve. So the basic kinds of conclusions we reached in that paper are that that top curve, measured relative to its starting point on this interval, yeah, okay, so that's obviously defined on this interval. Or anyway, I'm considering it's marginal there. So the kinds of conclusions that were reached via the BG technique in its basic form are things like absolute continuity. This is absolutely continuous with respect to, let's say, Brownian motion, standard Brownian motion, although I'm neglecting, as I've mentioned before, I think one tends to actually define the airy process at rate 2. I'm not worrying about those details in this talk. Yeah, right. So Brownian motion on the same interval. This is not a proof I've given. This is indicating the rough kind of conclusion that we were able to reach on the basis of this technique in its original guise. So, I mean, that's to say, if I take mu to be the underlying measure, that's Wiener measure on this interval, and then nu to be the measure that interests me, so that's going to be the law of this process defined on this interval, yeah, same interval, then, obviously it's the statement of absolute continuity that if a set has vanishing measure for one process, for the background measure rather, then it has vanishing measure for the process that we're studying. And of course, A is perhaps a measurable collection of continuous functions with some uniform topology. Kind of the setup. So equally, I'll be teaching this kind of material in a few weeks' time. We can characterize this statement by saying, it's a classical theorem, isn't it? That so this is equivalent to saying that you can choose for all epsilon and delta in such a way that I think delta epsilon tends to 0 with epsilon, such that the underlying probability being less than delta implies that the image probability is less than epsilon. So then that raises a natural question of quantification that's very important in applications where maybe you have union bounds over many events and you need to control them. What is the rate at which delta can be chosen to tend to 0 with epsilon? Is it possible in a given context to choose? These are the kinds of choices that are, epsilon, let me just say, I could write to some power, which would have to be less than 1 for simple reasons. Is it possible to choose it relatively close to, that would be a reasonably strong conclusion that this type of relationship exists. That's equivalent, if you like, the language of Brownian derivatives and what LP spaces they lie in. The statement I just wrote is equivalent to saying that for all finite p, not p is infinity, but finite p, is it the case that the Brownian derivative with respect to the measure in the underlying measure lies in all the LP spaces. Yeah, so, right, with BG analysis, with my students, Jake, Calvert, and Milland Higby, we proved, I think it was on the archive last year, a pretty strong relationship between what delta and epsilon can be in the context, you understand, of, let's just focus on the top curve in a unit interval. It's actually quite interesting to ask. It works for lower curves with different constants, and then it's interesting to ask what happens as you expand the width of the interval, but let's just keep it fixed. Yeah, quite a strong quantification that indeed establishes that this is true. Yeah, so it's that delta can be chosen to be epsilon. So I'm now going to multiply by something that will rise to infinity as epsilon goes to 0, but at a rate that is much slower than any inverse power of epsilon. It's the exponential of a large constant times log 1 over epsilon to the 5/6. Those are the details. 5/6 being less than 1. That correction term has the slow growth rate at 0, property I just mentioned. And that was quite a long argument. I won't attempt to give it now, but it was absolutely a Brownian Gibbs argument that gives that. And when you've got that, you're pretty robust for starting to, if you want to study the narrow wedge, that's where everything comes out of one point, all kinds of union bounds become available, because this is pretty strong control that the object in a unit interval looks Brownian in a pretty strong sense, quantified sense. We can use the language. It's quite a fun language as a phrase, and it has interesting ideas connected to it. The LPP energy landscape. So you see many statistical mechanical descriptions, spin glasses, Ising model, all kinds of contexts. You can, if you want, regard them as a complex energy landscape of hills, valleys, and connecting pathways given by a Hamiltonian and energy as things like e to the minus Hamiltonian, so you prefer to be whichever way around it is, let's say near the base of valleys, and you have some local movement. It might be something like a gradient flow with some random agitation moving you around this object. We can see, in certain regards, LPP in that context. So when you have complex energy landscapes, one of the natural questions that comes up is, there's a ground state, that's the energy minimum, that corresponds, or perhaps it's a maximum for us, to the geodesic. Can we have geometrically very distinct objects that are near ground states? Can we go on profoundly different routes through LPP, but still obtain roughly the best energy that's available? So the LPP version of this question in scale coordinates, if we go on the route from 0, 0 to 0, 1, this perhaps is the geodesic route, scale geodesic route. What I can do is, if I want to explore the degree to which other routes are available, then a particular aspect of this is to study the route at height 1/2. I can define the rooted scaled energy function that will report as a function of a real variable x. Well, Zx is going to tell me the best energy that's available on a route that goes from 0, 0, ends as before at 0, 1, and then it's constrained at the mid-lifetime x to go a half to go through x. So the maximum, the supremum of z of x is the best energy you can do. That is the geodesic energy, because there's no constraint. You go the best way you can with the geodesic. So an interesting question about the energy landscape is to say, suppose it's, probability, positive probability that the best route went to the right of the point 1. To what degree can we challenge that and find a near rival that goes on a very different route, that goes to the left of -1 at the midway time? So the profile would, in that case, look like that. This is the geodesic energy in scaled units. So in the event that the geodesic energy is attained to the right of 1, I have this kind of picture for Z, and that's the maximum level, so I'll never come back to it. But in the event of a near rival, an event that we tend to call twin peaks, I didn't draw that very well, but this is the kind of phenomenon that would occur. So imagine a given small sigma. What's the probability, we can ask, of this twin peaks picture? So this is related to the possibility of a rich energy landscape with near rivals in energy having fundamentally different geometric character. Yeah, okay, so this is a question that in work with Shishendu Ganguly, this particular aspect of the project with Shishendu, which addresses a dynamics project that is vaguely related, at least to that Wolf wave picture that I reopened with, vaguely related. Okay, but anyway, okay, the particular thing I'm about to say is essentially a consequence of the work with Jake and Milland, but it's going to appear here. Okay, so it says that the probability of sigma twin peaks, in the sense of the above picture, I hope it's clear what the event refers to. It's essentially sigma. I can write it, sigma minus little r of 1 for small sigma. So that the probability of this kind of coming back within sigma of your maximum at a distance horizontally at least 1 is behaving like this. I can tell you the kind of ideas that go into that. It's natural for the purpose of plotting z to actually, you see, I begin at the origin and I end at the origin at time 1. And then I'm interested in behavior at time 1/2. So there's 2 aspects of that. The energy I have going into time 1/2 from below and the energy from above. So I could plot it's as if there's a parabolic area ensemble that describes energy leading up to time 1/2 from 0. And then there's an independent energy that describes the situation coming back down from the top. Now, it's natural, in fact, for the purpose of analyzing the scale weight profile to draw the energy from the top upside down, to draw minus the function and to vertically align the function so it just touches at one point. And then that point of touch is where the energy, where the geodesic will run through. Because somehow that's how it works, that you only have one point of overlap. So the Twin Peaks is a phenomenon like this, where you almost touch, but a fair distance away. Now, it's not very hard to see if you believe that this is Brownian motion on a compact interval, and this is an independent one, then this difference function, or whatever it is itself a Brownian motion of rate 2. And then, at least intuitively, it comes down to the statement that if I take Brownian motion and look at its minimum on a given compact interval, say from 1 to 2, the probability that that is less than epsilon, this is maybe for definiteness chosen to be a Brownian excursion or something, or going off to infinity. The chance it does this is behaving like epsilon. It's not very difficult to see that with a resampling argument if you wish. Yeah, okay, so this is feeding into, and this is a nice enough question. Energy landscapes, it's, I suppose, a natural question. But the reason that it has a certain specific kind of pertinence is that Saurabh Chatterjee, let me summarize this material by this means. He had a monograph, or maybe it was the underlying papers that went into the monograph around 2008, in which he drew some very interesting connections between several topics. So one of those topics is superconcentration. What that means is, what sometimes classical technique like Poincare inequalities tells you that a certain fluctuation has a certain upper bound. But if a system actually has a behavior that fluctuates less than that, then it can be said to be super concentrated. So in LPP, we could draw a parallel with the central limit theorem and the n to the 1/2 fluctuation one would see in that, and identify the n to the 1/3 fluctuation we see in geodesic energy as being strictly lower than that, and say it's super concentrated. Another concept is chaos. So this is related to something that I haven't explained what kind of update I'll do, but in opening I was talking about the shimmering curves of the airy line ensemble. Related to that is the notion of taking Brownian LPP and doing some kind of dynamic update to it that will keep the individual curves looking Brownian, but have a dynamic process. If you do that, you can ask the question, how profoundly do things like the geodesic or other observables of interest change in response to the evolution of dynamic time? If they change rather profoundly in a short period of time, crudely speaking, the system is said to be chaotic. And then the other notion is related to what I've already been mentioning, the notion of many or multiple values. So the energy landscape of the system, does it have, this is not a Brownian motion, but an abstract representation of a high dimensional system and its energy landscape. Does it have many close rivals to the ground state? Ground state here, close rivals here, geometrically distinct. In a very crude sense, Saurabh's monograph says that these conditions for a certain class, fairly general class of Gaussian disorder that includes Brownian LPP in a certain sense, they are, the answer does this happen is answered the same way for each question. These conditions characterize one another. That is, crudely speaking, the conclusion of his monograph. So with Shishendu Ganguly, we're investigating, I don't think I will say very much about it. I don't want to keep you too long in it, and frankly, it could be a whole separate topic. So, but briefly, if we're taking Brownian LPP and doing dynamics, this is the project with Shishendu Ganguly. What's a natural dynamics to put on a Brownian motion? I want a process with an extra dimension of time whose equilibrium measure is going to be a standard Brownian motion. What's a natural way of doing that? Well, you can answer that question by retreating to the discrete and having little up-down moves, ticks and crosses, tick and cross up and down. And then I can dynamically update the ticks and crosses independently according to, in a new dimension of time, the ring times of a Poisson process. So for each one of these little symbols, I'm drawing a whole Poisson process. This is an initial condition. And then I just update the status of the symbol, tick or cross, at the ring time of the encountered process as time evolves in this direction. So here I independently update probability of half a half, it's cross, it's plus, it's plus, it's plus. So I have a shimmering system of crosses and ticks, and then I have a corresponding Brownian motion or white noise, discrete Brownian motion or white noise that is evolving in time. You can basically take that system and then put it through the classic invariance that takes Brownian random walk to Brownian motion and keep track of the updates, and you get the Ornstein-Uhlenbeck evolution on Brownian motion. That over time this isn't an entirely accurate description of what it does. It's more natural to look at it at the derivative level, in fact. But anyway, there is a natural update like this. So as you do this, you can ask the question, if I move on my classic route from 0, 0 to n, n, in Brownian last passage percolation, and I have this changing environment under my feet because it's quaking everywhere. Every individual Brownian motion is being slightly altered by the evolution of time. By time 1, there's a profound alteration. Anyway, it's a positive time beginning with a given instance of static Brownian LP. It evolves in time and stays at equilibrium, staying there at any given t. I can ask the question, how much time as a function of n must evolve in order to see it's in some sense a significant change in outcome? Now, there are different ways of measuring that. The one that's well adapted to the inputs coming from Shorov-Shashti's theory is the concept of overlap. Two paths with given endpoints have overlap given by the the Lebesgue measure, one-dimensional Lebesgue measure of the horizontal pieces that, oh, there they are. If I add up the lengths of those, that's a concept of overlap between two paths. So I can then study the geodesic, which I never really denoted in the talk so far. I call it gamma n. That's a function of t. So I can study overlap between the overlap at time t. I can define to be the overlap between these two paths, the sum of the lengths of the horizontal sections they share. So the overlap at time 0 is n, because the overlap with yourself is n. Oh, you're going up, I should say, you're going up to n here. Okay, diagonal direction. So yeah, we have a theorem that we should be coming out in the next few weeks. It says that the onset of chaos, which means when we start to really lose the condition that the overlap has order n, and it becomes much smaller than that. That occurs when t is of order n to the minus 1/3 on this scale. I won't try to say precisely our statement. When t is much bigger than that, the overlap is typically much smaller than n. When t is much smaller than that, it is bigger than c times n, with it is typically bigger than C times N. Yeah, all right. If I steal 5 more minutes of your time, maybe I could just tell you an intuition for why that's true. Yeah, the BG technique is technically undergirding it. Maybe I'll leave that for questions because it's actually a big topic. So I could, if anyone's interested, maybe after informally, I can give you some indication of why that's true. It's not clear why that exponent is there at the moment. Apart from that, I just mentioned other developments, probably very briefly. It's just, I'm afraid, going to be 1 minute apiece. So BG developments, this talk is intended to be a review and summary of progress with the BG technique. So we have positive temperature side of things that's worth a mention. The KPZ equation at time t is a kind of a softened up version of LPP problems. And there's a line ensemble. This top curve is the narrow wedge solution scale to the KPZ equation at time t. And then there's a line ensemble that satisfies a variant of the Brownian Gibbs rule, which has a softer interaction that discourages but does not forbid crossing of curves. So you get a picture that looks like this. This is the KPZ T line ensemble that was developed with Ivan Corwin, but after the zero temperature one, and has been the subject of a recent investigation by Xuan Wu, who proved a form of tightness for these curves. So it's a valuable technique at positive temperature. There's an interesting development, a recent advance by Dalburn, Ortman, and Virag that's I've mentioned briefly already. The accent, I forget. It's that the, yes, so, okay, so I've been working narrow wedge in these problems and telling you about the parabolic area that tells you about energies coming out of this given point, but we can come out of, get the Airy sheet, which has been a conjectural object that tells you the joint system of energies with a pair of endpoints, and all of it, or maybe more accurately, I believe 1/2 of it in some sense, but then there's an extra argument, can be read off from a very nice construction. There's an invariance that was identified that is related to work of Bian and collaborators, in which you solve a very interesting problem in which the you actually do an LPP problem in an environment provided by the parabolic area ensemble. So you, with a certain parabolic infinite initial condition, you are finding the maximum energy path through a copy of the parabolic area ensemble, and the fluctuation of that object is the value of this path. There's a couple of parameters here, a y endpoint here and an x that contributes to a certain infinitely distant initial condition to do with a parabola, and then a fluctuation in that tells you this energy. So that, in terms of the relevance to this talk, is that it's technically undergirded by the BG analysis that's quaking around as this parabolic area object is being controlled by BG analysis in the companion work of Duncan, Deverne, and Bannock-Varrick. And then, another nice recent work I'll just end with is a characterization of the airy line ensemble given its top curve of Yevgeny and Konstantin. So that basically says that if you know the top curve in a BG ensemble, you know everything. So the top curve is kind of king in that sense. And very crudely, you could say that you explore the top curve and then try to poke down and probe the curve below, making an infinitesimally sharp downward movement to a given level. And this way you either get blocked doing that or you don't. And it's the presence of the second curve that is getting in the way. So in that way, you can kind of read off from the statistics of the top curve information about the conditional law of the second one and build up the whole picture that way. So the BG technique is important in all of these applications, in whatever level of detail I attempted to describe them. And in a sense, I just want to end by kind of advocating it. It's central to my perspective, and I believe it's got more to say about LPP, KPZ universality at zero temperature, at positive temperature. There's more work to be done. It's an attractive technique, and I want to advocate it to a degree and draw it to your attention. Well, anyway, thanks indeed for your attention.
Well, let's thank the speaker. So I guess we can have a couple of short questions. I'm sure the speaker is tired, but hopefully he'll oblige. So I had a question. So the BG analysis, kind of at its very core, is a comparison statement between these sort of conditional Brownian bridges, conditional staying above some curves, random ones, and the usual Brownian motion or Brownian bridges. How far do you think you can push this comparison? So, for example, can you gain any sort of, Hausdorff dimension of exceptional times, or local time for Brownian motion level of comparison, or is that completely wild?
I mean, it's true that, an underlying quantity that's important is what can be called the acceptance probability, which speaks to the distinction you make between the free Brownian motion with the endpoints and the actual conditioned motion. That the point is that the candidate comes in free, but they have to pass a test. Do they avoid the curve below? What's the probability of that? If you call that the acceptance probability, then one of the challenges of the basic analysis that was done in the first place was to show that that's an object that is not deteriorating towards zero, piling up towards zero as the pre-limiting parameter of the model in scaled coordinates. N tends to infinity. At this stage, though, although in fact sometimes the curves do approach one another, various tricks in which slightly more sophisticated variants of the BG resample, still the underlying BG technique, but different resamples in which information is given or withheld in a slightly more cunning way, permit you to, as it were, lift off the if you happen to be jammed in very close at one point, you can do tricks to back out a little bit and you want to withhold a little bit of information so that you've got the freedom to move around, but not too much so that you stop being able to track anything explicitly. And by doing this, you can kind of come up with variants where the acceptance probability statistics improve. That's led to outcomes like that theorem with Jake and Millen that are now giving very strong information about the relationship between epsilon and delta. So your question was about Hausdorff dimension of exceptional points. I don't know if it's the precise context you mean. That is a very nice range of questions you can ask about things like the airy sheet. When do you have exceptional behaviors? We had a question, was it from Evan before the break, about what happens in this tree picture when you have exceptional situations with non-unique geodesics? What's the Hausdorff dimension of that set? What's the Hausdorff dimension of the set where Johansson's conjecture fails? Well, I should explain what I mean by that. You can do a dynamic, I was starting at 0, 0 and going up to time 1. I can treat that time 1 now as a variable that lifts and ranges between 1 and 2. And then if I draw the top curve in the airy line ensemble, the parabolic airy 2, I can watch it shimmer and vary as a process. Does it have exceptional moments at which its Hausdorff dimension, at which it violates Johansson's conjecture? That's our forthcoming work with Konstantin, Ivan, and Millen Higby to identify the Hausdorff dimension of that set. So, I don't know if that's exactly the same sort of Hausdorff dimension you meant, but BG analysis, I think, is also undergirding that project. There's been work with Eric Bates and Shishendu Ganguly that's examining Hausdorff dimension questions. I know that the Toronto group, Ballin and Duncan, are very interested in these things as well. The BG technique, I think is actually indirectly playing an important role in all of this, I think.
Thank you.
I have a question, if I can. I'm Martin.
Hey.
Thanks very much for the very nice talk. So when you described this dynamic discrete version of the line ensemble, that was exclusion essentially, right? When you replaced the two kinds of figures according to a Poisson process.
Is that
and we were
right?
looking for the overlap. Is that not an exclusion?
Yeah. Well, let me think what I actually said. Well, okay, the only moment in the talk I actually mentioned, I was just saying that, no, well, that would be more just like you could do exclusion. That would be a dynamic update. The particular one that I was proposing was one that simply is in the style of the updates you see in noise sensitivity around critical percolation. So you just have a discrete set. You have a finite set and it's assigned open and closed status, and then ring times of independent Poisson processes, you update those.
Okay, then maybe, because it really looked like the height function of an exclusion process. And my question was going to be how your result then could possibly relate to the mixing time results we have seen recently.
Well, I'm not sure that it is quite the same update. You mean mixing time when you start two different random walk initial conditions, and then you do kind of an exclusion dynamic and see how long they take to couple or something like that?
Something like that, yeah. Yeah, there have been some results about this, and I thought it's related, but maybe I was wrong.
I think there are interesting connections to, you can do updates on the ensembles that I was hinting at with that little thing I opened with in the second part, where you can do a dynamic on an individual curve where you pick a random time and then flip up or down like this. If you're able to do, maybe if you're in a down-down configuration, you can't flip at the moment. But if you're in a down-up configuration, you can flip into this and then the other way around. And then that's a dynamic that might be related to exclusion. So you could then mention doing that dynamic on something like a tiling model, a lozenge model, and then asking, how do I have to scale that dynamic to map onto something that is going to shimmer around when I map onto an airy line ensemble? And then can I define a dynamic on the airy line ensemble by doing that? You can then ask questions about, if you've got that dynamic on the airy line ensemble, it will specify in a scaled limiting sense a evolution for LPP energies, scaled LPP energies, and you can ask what the relationship between that is and the work I'm doing with Shishendu, in which we begin with a natural dynamic on the underlying microscopic Brownian motions and Brownian LPP. These are all very open directions at this stage, and quite interesting problems, I think.
Okay, thank you.
So are there any other questions? Okay, well, let's thank the speaker again. Thank you everyone for sticking around, and have a good weekend. Thank you, Alan, for a great talk. Okay, so I guess people can just leave. That's what I plan to do. Okay, see you all.
I did, by the way, put there is the link for the Pacific Rim conference. You might just want to look at that. Like, we do have some very good speakers in probability and more broadly. And if you're interested, please do take a look, and you can register and get information about Zoom links coming. It's in the first week of August.
Okay, well, thank you. I'll circulate that in the Columbia probability channels.
Oh, that would be great.
Yeah. Thank you very much again. Have a good weekend.